You know, we hear it all the time. Our oceans are just filled with plastic. But when you get down to the really, really small stuff, the nanoplastics, we've basically been flying blind. For decades, our entire understanding of how dangerous these particles are was, well, just a guess. We'd never actually seen what's really out there. Until now.
So here's the deal. For years, whenever scientists wanted to study how these tiny plastics might be harming marine life, they had to use particles they made in a lab. And that created this huge blind spot. It means we were building our entire picture of nanoplastic toxicity on a model that, what if it was just completely wrong? The big question was, what does the real stuff actually look like? And this really gets to the heart of the problem. On the left, you see these perfect, clean little spheres that scientists have been using in labs for decades. But on the right, that's the real world. A global ocean filled with plastic that's been weathered, battered, and broken down into who knows what kind of shapes. We weren't studying reality.
Okay, so to solve this mystery, scientists needed a totally new way to see. They had to figure out how to pluck these impossibly small particles out of the vast ocean and get them under a microscope. And the solution they came up with is just, it's so clever. It's an ingenious laser-powered bubble trap.
This is the key right here. The whole technique is called shrinking surface bubble deposition, or SSBD for short. See, the biggest challenge with finding nanoplastics is that they're so incredibly diluted out in the ocean. It's like looking for a few grains of sand in an Olympic-sized swimming pool. This bubble method is designed to solve that exact problem.
So here's how this amazing little trap works. First, a laser zaps a water sample to create a teeny tiny bubble. Now, the heat from that laser creates this powerful microscopic whirlpool. It's a thermofluidic flow that sucks all the nearby nanoplastics right onto the bubble's surface. Then, they just turn the laser off, the bubble shrinks, and poof, it deposits all the plastic it captured into one tiny, concentrated spot for us to finally see. It's literally finding a needle in a haystack.
And here's where it gets really clever. Those silver nanoparticles they use, they're not just there to make the bubble. They get deposited right there with the plastics. So later, when scientists shine another laser on the sample to analyze it, that silver acts like a chemical spotlight, massively cranking up the signal from the plastic. This lets them not only see the plastic shape, but also get a chemical fingerprint that tells them exactly what kind of plastic it is. It's an amazing two-for-one solution.
So, the trap was set. The samples were gathered from oceans all over the world, and this new technique was put to the test. For the very first time, we were about to get a clear look at the true face of nanoplastic pollution. And the results? They were just stunning. This is what they pulled from the water off the coast of California. They're not spheres at all. They're long, thin nanofibers of nylon. These are probably tiny threads that broke off of fishing gear, or maybe even from our synthetic clothes going through the laundry. A totally different shape than anything we'd been studying.
And the discoveries just kept on coming. In water from the Gulf of Mexico, they found this, a jagged, beat-up-looking flake of polystyrene. You can practically see the history of it, getting battered by waves and sunlight, breaking off from some bigger piece of plastic. And again, it looks nothing like those perfect little spheres from the lab.
And maybe the most surprising find of all were these incredibly complex, what they call ball and stick structures. These are made of PET, the same plastic in our water bottles. I mean, look at that thing. It looks more like something out of a chemistry textbook than a piece of pollution. The sheer variety of shapes was way beyond what anyone had imagined.
So this is the bottom line, right? On one side, you have the simple, uniform, perfect spheres that we thought we were dealing with, and on the other, you have the actual reality of the ocean, this chaotic mess of fibers, jagged flakes, and weirdly complex structures. The difference is just staggering. We weren't just getting the details wrong, we were looking at a completely different beast. And listen, this is way more than just a cool visual. The shapes of these particles have huge implications for how they interact with living things. It turns out, when you get down to the nanoscale, shape is everything. The research paper puts it pretty clearly. A particle's toxicity is directly connected to its shape. Just think about it, right? A long, sharp fiber is going to interact with a living cell very, very differently than a smooth little ball. One might just bounce off, while the other could act like a tiny dagger, causing some real damage. And that means that decades of our research into the harm caused by nanoplastics might need a serious reevaluation. All those studies that concluded certain levels of spherical plastics were safe, well, that might not be true for the jagged flakes and sharp fibers that are actually out there. We've been running our experiments with the wrong puzzle pieces. But this breakthrough isn't just about what we found. It's about the incredible tool we have now. This bubble trap technique gives environmental scientists a powerful new lens for looking at pollution, and it's honestly going to change the entire game.
And what's truly mind-blowing is the sensitivity. Some of the older methods for doing this required filtering thousands of liters of seawater just to get a sample you could measure. This bubble trap, it works with less than a single milliliter of water. That is an absolute game changer for monitoring our oceans quickly and easily.
So what does this all change? Pretty much everything. It means we can do rapid environmental monitoring all over the world. It forces researchers to use realistic particle shapes in their studies, which means we'll get way more accurate data. And that data can finally lead to smarter regulations. It even helps us track how these tiny particles travel and build up, from the surface all the way to the deep ocean.
For the longest time, we've been fighting an enemy we couldn't even really see. But this new technique has finally given us a clear picture of what we're up against. So the real question now isn't just what these particles look like. It's now that we can finally see them for what they are, how is that going to change the way we fight back?